Hello. So in this video I want to talk about de Moivre's theorem. Um, it's actually not called de Moivre's theorem in the FE review handbook. The formula is actually located under polar coordinate system. I just search polar coordinate, Control F to bring up the search bar, and it's under the mathematics heading, page 23 in this edition. This is the 2013 edition of the FE Review Handbook. And as you can see here, it's outlined right here. And basically, you would use it when you are looking for a complex number raised to some power. It's basically a derivation done for you. So let's look at a quick example. So we have two terms here multiplied together. There are two complex numbers. Basically, we're going to have to apply de Moivre's theorem, or de Moivre's equation, to each of these terms. So I'll call this first one z1, and I'll call this second term z2. So we'll compute each of those individually using de Moivre's theorem and then multiply them together. And when I multiply them together, I'm actually going to use this. There's an equation here. I actually posted an example of this in the previous video. It's actually right here. So instead of distributing manually, it's already derived for you. So once we get to that point, we'll apply this formula right here. So for this first term, z1, which is 2 times cosine pi over 6 plus j sine pi over 6 quantity raised to the fourth power, we can use this guy here, and when we plug all those values in, we'll get 2 to the fourth. The fourth power gets multiplied into the angle, so it'll be 4 pi over 6 plus j times sine of 4 times pi over 6. And this we can simplify to 2 to the fourth is 16. Cosine of 4 pi over 6 is cosine of 2 pi over 3, which is negative 1/2, plus j times sine of 2 pi over 3 is root 3 over 2. And finally, when we distribute, we get negative 8 plus j times 8 root 3. So that's our z1. Our z2, using the same equation, let me rewrite this, 3 times cosine of pi over 3 plus j times sine of pi over 3. And this is raised to the second power. So again, we'll just distribute that 2 to the radius, so 3 squared times cosine of 2 pi over 3 plus j times sine of 2 pi over 3. So then this will reduce to 9 times cosine of 2 pi over 3 is negative 1/2, just like before, plus j times sine of 2 pi over 3 is root 3 over 2. And this will finally reduce to negative 9/2 plus j times root 3 over 2. So z1 and z2 can be easily found using de Moivre's theorem. And in order to multiply z1 and z2, we would again refer to this equation here. I did an example of this again in a previous video, so if you're not familiar with it, you can check that out too. But it's pretty simple. So the equation is R1 times R2 times cosine of theta 1 plus theta 2 plus, let's see, cosine of theta 1 plus theta 2 plus j sine theta 1 times theta 2 plus j sine of theta 1 plus theta 2. And in our equation, theta 1 would just be these first two angles in the z1 term, and theta 2 would be the thetas in the z2 term. So R1, so this is the equation we're using. This is z1 times z2, which equals this. So R1 is 9 times R2 is 16, and I got R1 and R2 from this form here. I know I distributed the 9 through, but when you have it in this form, this is R times cosine of theta plus j sine of theta. It's in this form. This form here is x plus jy. So when we refer to this guy here, we know r right away. So that's how I found 9 and 16 for R1 and R2. So cosine theta 1 is pi over 6 plus theta 2 is pi over 3 plus j times sine of pi over 6 plus pi over 3. So 9 times 16 is 144. Cosine pi over 6 plus pi over 3 is, let's see, 4 pi over 3. So cosine of 4 pi over 3 is negative 1/2 plus j sine of pi over 6 plus pi over 3 again is 4 pi over 3. So again, so this here is 4 pi over 3. So sine of 4 pi over 3 is root 3 over 2. And finally, I mean, we can leave it in this form, but if we distribute it through, we'll have negative 72 minus j times 72 root 3. So this would be our final answer to our original equation, or original question here. Okay, thanks for watching.